Right, so we're going to continue with our introduction of elements, and this is the last one we're going to have for this course, and we've sort of ignored it until now, but we have to introduce our final element of our basic molecules we're going to talk about, and this will be including nitrogen. So the two groups of molecules that have nitrogen in them that we're going to concern ourselves with are amines and amides. And they're very, very similar to two other groups we've already seen. So the first thing I want you to do is turn to that list wherever you have it of your priorities, and we're going to add these two to our list. Okay, so in the back of your notebook or on a card or wherever you've been writing this, at the top of your list at the moment should be carboxylic acids. And maybe you wrote esters on the side of it, and that's fine. So carboxylic acids and then esters. Right underneath esters, you should write amides. So it's going to be right up there with the ester group. So amides just below esters. Underneath that, you have the others with only two bonds to a non-carbon atom or non-hydrogen atom. And that was our aldehydes and ketones. Okay, and those will be exactly where they are. We're not going to move them. And underneath aldehydes and ketones, you should have had alcohols, only one bond to oxygen. And just underneath alcohols, I want you to write amines. Okay, the first word here. So we added amides just below esters, and now we're going to add amines just below alcohols. And that's going to complete our list, right? Those are all the ones I want you to know. Those are complete. And we'll describe what amines and amides are in just a moment. But now you know where they fall in the list. So an amide is very similar to an ester. That's why it's just below it. All we've done is replace the oxygen with the nitrogen. And you'll see some pictures in a minute. And the amines are analogous to the alcohols. Again, we've replaced the oxygen with a nitrogen. That's the only differences. But those differences have consequences. All right, so let's start out with the amines first, the simpler of the two. So this is the nitrogen corollary to an alcohol. Right? So if we had an alcohol there, there's an OH. And why was there only an H on the O? Why do we always have just OH and not additional things added to the oxygen? Well, because oxygen generally makes how many bonds?
Two.
Two, exactly. So when we use nitrogen in place of the oxygen, how many bonds does nitrogen normally make?
Three.
Three. So if I'm going to add a group on, and instead of having an OH there, and I use a nitrogen, what organization will it have? It won't be NH. What will it be?
NH2.
NH2, exactly. We need an extra bond to the nitrogen, so it'll have two hydrogens on it. Right? And if you look at the list I have here, where I list them in their degrees of complication, basically, we have a primary amine, which is simply what we just described. It's called an amino group, much like we called an OH a hydroxy group. This one's called an amino group, so that's how it'll be named when it's a substituent, simply amino, just like you called an OH a hydroxy when it was a substituent. Right? And then if we have more than one thing on that nitrogen, right? So something else attached to it, say another R group, another carbon chain, then there'll only be one H left. This secondary amine is analogous to what thing we did with the alcohol. What would we call it when we did that with the OH group instead? When you didn't have the H on the O and you attached some other R group to the O instead, what did you call that? It was an ROR.
Is it an ester?
Not an ester, but
Ether.
an ether.
Ether.
Exactly, that was an
Yeah.
ether. Right, so this secondary amine is much like an ether, where instead of having just the electronegative atom, like the O or the N there, with its complement of hydrogens, we've replaced one of those hydrogens. In this case, there are two to replace. We've replaced one with another R chain. Right? It's still called an amine in this case, but it's equivalent to having the ether formation. Right? But as far as the nitrogens go, it's still called an amine, but we call it a secondary amine. That's what the two here indicates. Right? So I have a secondary amine. And then if I replace both hydrogens...
I'm sorry. I don't want to stop you, but before we go further, can you remind me where the amines go in the priority list again, please?
Just below alcohols.
Alcohols,
They're
okay.
very, very
Thank you.
similar to alcohols. Right? So the
Before the double bonds.
what was that?
Before the double bonds?
Above the double bonds, yes.
Okay. Okay.
So
Thank you.
a secondary amine is when we've replaced one of those H's with some other R chain. So there's only one H left. So this nitrogen is now spanning between two chains of carbons, and it still has one hydrogen. If I replace that hydrogen with a third chain, now this nitrogen is making three bonds to three different carbon chains. And this is called a tertiary amine. So the degree here, right, the primary, secondary, or tertiary, tells me how many non-hydrogen things is this nitrogen bonded to. Well, we know nitrogen makes three bonds, so if it's bonded to two H's and only one carbon chain, that's its three bonds, it's a primary amine. If it's bonded to two non-hydrogen things and only one hydrogen, that's a total of three, it's a secondary amine. And if it has no hydrogens on it, bonded to three carbon chains, then it's a tertiary amine. Right? And then the fourth possibility, since it is nitrogen, and I want to remind you what this looks like, let's briefly draw, or very quickly draw, ammonia's Lewis structure. Just very, very simple. Right? Remember, nitrogen brings how many electrons in its valence shell?
5.
5, and each hydrogen brings
2.
1, right? 1 in its valence shell. And if you add those together in ammonia, how many total valence electrons?
8.
8. So what will we draw? We draw nitrogen first. We draw 3 single bonds, right? 1 to each hydrogen. That's used how many of our 8 electrons?
6.
6. What do we do with the other 2? Where should we try to put them first?
The central atom.
No, that's not the place we try to put them first. We try to put them on the extremities first, right? Remember how we did that with oxygens and chlorines and everything else. So we try to put them on the hydrogens, which is impossible because they already have 2. Right? So then our next step is the only place we could put them is on the central atom. Right? Don't skip over that step. We can't do it here, but don't forget about that step. Right? So we put the 2 extra electrons on the nitrogen, giving it a lone pair. What would its electronic and molecular geometries be?
Electronic would be tetrahedral, but molecular would be trigonal pyramidal.
Exactly. So electronically, there are 4 regions that contain electrons, right? So there's the 3 bonds to the hydrogens, and then there's that lone pair. It's another grouping of electrons. So they occur in 4 different groupings, and those are going to be as far away from each other as possible, and that would be tetrahedral. Absolutely right. And then for molecular geometry, we take into account the lone pair, but we don't count it as far as a thing. It's not a real atom, right? So in that case, it would be the tetrahedral missing one of its points, right? So it looks like a 3-sided pyramid, right? So it's trigonopyramidal, exactly right. Right? But in the case of this nitrogen, we do have that lone pair, right? That was the point of doing that. And if a hydrogen were to show up, and when I say a hydrogen, in this case, I mean just the proton, no electrons around it, just a naked proton. So that's a hydrogen ion, H+. If that were to show up, couldn't it make a bond with that lone pair on the nitrogen to fulfill its orbital of 2? The nitrogen would still have 8 around it, right? It would still be happy. It has 8 total. And the hydrogen that just showed up would also have 2, and everybody would be happy. However, there'd be an extra positive charge here, because just the proton showed up. It didn't bring any electrons to this party. What did we call that before? What kind of bond was that?
Coordinate covalent.
Coordinate covalent, right? We often said oxygen was the culprit for doing that, but also H+, since it also needs 2 more electrons to fill its shell. And so if you look at the bottom here, this NH4+ is a nitrogen single bonded to 4 hydrogens, but as a group, this whole thing has 1 extra proton compared to its number of electrons. So overall, it has a positive charge. So we call this a what? All these terms are coming back. So what do we call this thing as a group? It's got multiple atoms and it has a charge.
Polyatomic ion.
It's a polyatomic ion, exactly. So we've seen these things before, right? But now we're saying this one's going to be called a quaternary. Remember, we followed our pattern here: primary, secondary, 2 things bound to nitrogen, 3 things bound to the nitrogen that aren't hydrogen. This time we have 4 things bound to it. They happen to all be hydrogen in this case, so it's not an amine anymore. It's just called an ammonium ion, right? Because it's ammonia that's got an additional proton attached to it. So it's an ion now, and it's called the ammonium ion, right? What kind of geometry would it have, electronically and molecularly?
Both would be tetrahedral.
Both would be tetrahedral, absolutely right. So the nitrogen is making 4 single bonds, that's tetrahedral. There are no lone pairs anymore, so molecular and electronic geometries are the same. The charge doesn't change that, right? It just happens to have 1 fewer electron than it does protons because of that coordinate covalent bond that was made by the proton. So excellent. So we know what primary, secondary, and tertiaries look like now. So if you're counting the number of bonds nitrogen makes that are not to hydrogen for primary, secondary, and tertiary. I threw in the quaternary at the bottom to remind you that this is possible for nitrogen. It can gain this positive charge and make another bond. Right? Carbon is not going to do that and make 5 bonds, but ammonium and nitrogen atoms can do this. Right? And the other thing I want to remind you before we start, or introduce to you before we start, is how do we write our formulas, right? So when we started making formulas, or from molecules, we wrote down the molecular formula. We start with how many carbons does it have? I don't know, let's call it N, right? We'll have a stand-in for the number of carbons. We'll call it N. And then how many hydrogens did it have? What do we always start with? What's the subscript on hydrogen?
2n plus 2.
2n plus 2, exactly. And then what do we do with that after we write down 2n plus 2? We make some adjustments. What adjustments do you know of?
We count sites of unsaturation.
We count sites of unsaturation. What constitutes a site of unsaturation?
Ring or a double bond.
And each of those, what would I do because of them?
Subtract 2.
Subtract 2 hydrogens, right?
Yes.
Okay, anything else that would adjust the number of hydrogens?
What's it called? Fluorines and the halogens.
Halogens would do that as well. We briefly skipped over triple bonds, but for every triple bond, we would subtract 4, right? Because it counts as 2 sites of unsaturation on its own. And then you said halogens, exactly. So these on the right, that column with fluorine, chlorine, bromine, iodine, all of those will count as not a site of unsaturation, but they've taken the place of a hydrogen. So you'd subtract 1 hydrogen from the formula for every halogen you see, because they've taken its place. And then we're going to add one more thing I need you to know for that formula, as far as this class is concerned, is when we have a nitrogen. When an oxygen is present, it had no effect, right? But when a nitrogen is present, because it has that extra bond that oxygen doesn't, we have to add 1 hydrogen to the list, right? So for every nitrogen in the formula, you have to add 1 H. Okay, so you have this long formula now of starting of 2n plus 2, n being the number of carbons, subtracting 2 for every site of unsaturation, with, remind yourself that triple bonds count as 2 sites, subtracting 1 for every halogen, and now adding 1 for every nitrogen. And that's going to complete our formula. And so when you see an odd number of hydrogens, there's some possibilities. Either there's a nitrogen present, because 2n plus 2 can't be odd, or there's a halogen present. So those are the things that can make it an odd number. So keep that in mind when you're writing your formulas.
One quick question. You said nitrogen made 3 bonds, right?
Nitrogen makes a total of 3 bonds normally. It could make 4 if it has a positive charge. It uses that lone pair of its to make another bond.
Okay, thanks.
Right, carbon could not do that. It didn't have a lone pair. Okay, so let's start naming these things. This is our last 2 groups of names, these amines and amides. So let's do amines first, since they're rather simple. So it's basically like an alcohol, except it's a nitrogen instead of an oxygen. That's the only thing we've changed here. Okay, so let's play the game the same way. We're going to find the longest continuous carbon chain to which the nitrogen is bonded. We did the same game with alcohols. We found the longest continuous chain to which the oxygen was bound. So play the same game. So in the first one here, right? What's the longest continuous chain to which the nitrogen is bound? That means you have to include this carbon, right? Well, that's fairly simple, right? It's just these two carbons. This is not a carbon, don't count it as a carbon. So it's just 1, 2, right? And why did I pick this one as 1 and not this one as 1? To put this thing on the lowest number possible, just like you did with alcohols, right? And then we changed the ending, just like we did with alcohols. We changed it from E to OL when we made an alcohol. Here we changed it from E to amine. We put the whole name in there, amine, right? Makes it rather easy to remember or recognize. So this one here would have 2 carbons, so it's ethane. We drop the E from ethane and add amine. So it's ethanamine. Rather simple, easy to do. Okay, the second one, equally as simple. We just count the longest continuous chain that must include this carbon, because that's the one the nitrogen's on. So it's all 4. So that would be butane. Drop the E from butane, add amine, so it's butanamine, but I need the 2 this time. I have to tell you where the nitrogen is. Right? Here I didn't have to tell you because no matter which carbon it's on, it's number 1. Here it could be on 1 or 2. This would also be 2, and this would be 1. So it could be on 1 or 2. So there are other options. The 2 is necessary. Right? And then like we've done with all the other examples, what if there are 2 of them? Right? We learned how to do diols and dicarboxylic acids and so forth. So we're going to do the same thing here. There are 2 amines this time. Right? And so the number of carbons is 1, 2, 3, 4. These are not carbons. So 1, 2, 3, 4. So it makes it butane, but not butanamine, butane diamine. And I left the E in there this time to make it pronounceable, right? Because this is a consonant. So butane diamine, and where are they? They're on 1 and 4. I do have an issue.
I have a question.
I'm sorry, go ahead, and then I'll ask my question.
Okay. What is the di for again? Is that because you have 2 NH2s?
That's exactly right.
Okay, thank you.
Right. Just like when we had 2 OHs, we called it a diol. Right? And I put the di in front of the thing of which I have 2. Right? So it wasn't 2 butanes here. It's not a dibutane. It's a diamine.
Thank you.
Okay. So my concern with this drawing is what? Somebody have an issue with this drawing? I have several issues with this drawing. And I left it in here so I can point this out because I see this on student drawings often on exams and when you're trying to explain things to me. But what 2 main issues do you see with this drawing?
On the left side, it looks like the carbon chain is bonded to the hydrogen instead of the nitrogen.
Right. So the right side is clearly going to the nitrogen, but the left side, it looks like the carbon's going to the H's or the 2, which doesn't make any sense. So we should have written this the way this methyl group was written with the hydrogens on the other side. It should say H2N, which would make more sense here, like the way this one's written. So good, I agree with that one. What's the other issue I have with this thing? And it's not the color. Look at the numbers.
Is it the E? Oh, no. I thought it was the E in butane diamine.
No, the name is fine. I'm talking about the structure itself, how it was drawn. Look at the numbers. These 2s are supposed to be subscripts, like the 3s here, and like this 2 here. They're written at the same size, which is just laziness in this drawing. I know we do that when we're typing things back to each other all the time, but if you can make it a subscript, it should be, and that's the proper way to do it. It's telling me there are 2 hydrogens, not a big capital 2 out here. It's a subscript, right? So that's the other issue I have with this drawing. But so be careful when I left it in here to point that out, but be careful when you're drawing these things, you do them properly, right? Now, on all our drawings previously, we've made the rule that you don't have to draw H's on carbon. Like I drew them out here, right? But here I did not, and you don't have to. You don't have to show hydrogens on carbon, but you must show hydrogens on every other element. So these H's here are necessary. You have to show me that. These here are necessary, just like they were on oxygen, right? But if it's on a carbon, you don't have to show it. It's the only one you get to do that for, okay? So these numbers I keep putting in front. This one didn't need a number, but this had a 2 and this had a 1 and a 4. Those are essentially the address, or the addresses, plural, of where things are. Right? That's all that means. It doesn't necessarily need to be a number. You may know someone who lives at a certain apartment with a letter in the name, right, instead of a number, or their address is a letter instead of a number in the front of their street address. And that's perfectly valid. And it's the same thing for chemical formulas or chemical names. We can have an address that's a letter, and that's shown at the bottom. So in this molecule here, this is an amine again, but what kind of amine is this? Is it primary, secondary, tertiary? What do you think?
Tertiary.
What makes it tertiary?
It's bonded to 3 non-hydrogens.
The nitrogen is bonded to 3 non-hydrogen. Thanks. I agree. That's a tertiary amine. What about the other 3 at the top here?
The top left is tertiary. It's primary.
This one's primary, right? What about this one?
Primary.
It's also primary because it's
Yeah,
nitrogen.
they're all primary.
They're all primary, right? So even both of these ends, they're both primary amines. So all of these are primary and this one's tertiary. If we just had one other H here instead of none, it would be a secondary amine. So we have a problem here. What is the longest continuous carbon chain, that's our rule, that this nitrogen is bound to? Well, you have 3 options. There's this one, or this chain. Which one do you think we're going to pick?
The butane.
The longest chain, exactly. So that's going to be how long?
4.
Right, this is number 1, because that's the lowest number in this chain to which you can attach it. So 1, 2, 3, 4. So its parent name will be butane, but it's got a nitrogen on it, right? And it's an amine, so I changed the ending from butane to butanamine. The 1 indicates where it is on the butanamine, just like this was on 2 of butanamine, right? And then I have 2 methyl groups. What's their address? They're not on any of the carbons. They're on the nitrogen. So that's its address, right? They're not on carbon 1 or carbon 2 or 3 or 4 like these were on carbons. But these methyl groups are on the nitrogen. So that's its address, N,N-dimethyl. These N's in front are simply just like the numbers, they're just an address. We often write them in italics to indicate that. Everybody okay with that? It's nothing new. Well, it is sort of new to you, but it's nothing unusual. It's just another way of representing the location. Right? And we'll do lots of examples of this if you want. Right, any questions so far on naming these? Okay, so let's do a couple examples. How about this first one? Very similar to the one you just did, but it's not the same molecule. So follow your rules. Look for the highest priority thing. Well, I don't see any double bonds, I don't see any esters or anything like that. It must be the nitrogen, right? So it's an amine. So it's clearly I want to find the longest continuous chain that is attached to this nitrogen. And I can't count through the nitrogen because this is not a carbon. So you have 3 choices. This is another tertiary amine. So pick the longest one. So how do we start this name?
Propane amine.
Propane.
Propane, and then we change the ending to amine, so it's a propane amine. Where is the amine? If this is your propane, where is it? You need to locate it.
It's on 1.
It's on number 1 of the propane, because it could have been on 2. Right, so it's definitely on number 1 of a propane, so it's 1 propane amine. What substituents do you see? And a great way to do this when you're naming these things, and this was true all along, some of you have been doing this, circle what you've named so far. So if I circle this propane here along with the nitrogen, that's propane amine. And I have some substituents. What are they?
N-ethyl,
Ethyl.
N-methyl.
Right, there's an N-ethyl, N is the location, and it's an ethyl group. And there's an N is the location again, methyl group. Right, which of those comes first alphabetically? The N is not something you alphabetize, it's just the address, it's just a number. You can alphabetize ethyl and methyl. So which one would come first?
Ethyl.
Ethyl. So we're going to do N-ethyl first, followed by N-methyl, and then 1 propanamine. You treat these N's as if they were just another number, so they get dashes around them just like this one does. I know it's a letter, not a number, but it's actually an address. So whatever the address is, treat it like it's another number. Right? So they're locating the positions of these two substituents. I can't call it NN because these aren't the same thing like I did on the previous slide. Okay. Everybody okay with this name? Or have any questions? This one's fairly easy. Okay. All right, here's a slightly more complicated one. It's really the same problem. You just have to put different words for different substituents. So the first step, locate the highest priority thing. Well, I see a benzene ring, but where do benzene rings fall in your priority list? If there's something else around, where do they fall?
Everything else.
With everybody else, right? They have no priority over this nitrogen, right? So the nitrogen still is our highest priority, so it's going to be an amine, right? So which carbon chain should I choose from? Well, one's connected to this nitrogen. So either this one or this one, right? So what is the longest continuous chain connected to the nitrogen?
Ethane.
Ethane?
Yeah.
Somebody said propane, right?
I did, yeah.
I see 3 as well. Do you see this? 1, 2, 3?
Yes. I see it now.
Right. So don't forget, you got to go as far as you can. You can't go into the ring. Remember, we can't go in and out of carbon rings. So 1, 2, 3. And why am I choosing this side as 1 and not this side as 1?
Because of the nitrogen?
Well, the nitrogen's on 2 either way.
Because of the ring.
Because of the substituent, right? I'm going to give this substituent number 1 location rather than number 3, because either way, nitrogen gets on 2. So I've met my priority. Now I want to give the lowest numbers possible to all the substituents. So good. This is 1, 2, 3. So it's going to be called what? Propane. We changed the ending to
Amine.
propane amine, just like before, right? And then what's on my propane amine?
Phenyl.
I have a phenyl group, right? Good, a benzene ring as a substituent. This is not part of the substituent, right? This is number 1 carbon of the main chain. So it's just a benzene ring as a substituent is a phenyl, excellent. And its location?
On 1.
So a 1 phenyl and
N-methyl.
an N-methyl, exactly. Which of those comes first alphabetically?
The methyl.
The methyl, right? The N is not something you alphabetize, right? So the methyl, so you're going to have an N-methyl, then a 1 phenyl, and the 2 is the location of the amine on my propane amine.
So the carbon is 1 when you named it that way, with the one closest to the phenyl, is because of the phenyl ring.
Right.
Is that
right,
why?
because that was the first substituent on this chain, right? Because this is not on the chain, it's on the nitrogen.
Gotcha.
Right.
I see.
So
Thank you.
this had no effect on the numbering system.
Okay.
Okay, good. So both of these are amines. That's great. You guys have got it. Find the longest chain to which the nitrogen is attached. And you notice if we don't have a primary amine, as in the case here we had a tertiary, you had 3 options. When you have a secondary, you notice there's 1 H left. It's a secondary amine. You had 2 options to choose. You correctly chose the 3 carbon chain over the 1 carbon chain. But when you have amines that are not primary, you're going to have options. You got to find the right parent chain. Okay? And like everything else we've introduced.
I have a question.
Sorry, go ahead.
Would you name the other methyl, or is it not a substituent because it's part of the chain?
Well, we did name it as a substituent. It's the N-methyl substituent right here.
No, I mean the methyl on 3.
Number 3 is not a methyl. It's 1, 2, 3. It's the end of the main chain.
Okay.
I mean, yes, you can visualize it as a methyl protrusion, I guess, but it's actually the 3rd carbon of the 3 in the main chain, right? So it's not a substituent as far as the name's concerned.
Okay.
Right, good question though. Right, so in these cases, we've gone over how to name it as an amine, but like everything we've talked about except the esters and carboxylic acids, what if it's not the highest priority around? Right? So what if something like this is around? What's the highest priority thing you see now?
The carboxylic acid.
The carboxylic acid. It's the highest priority thing on your list. That means that nitrogen, which would make it an amine, is not going to make it an amine this time. It's a substituent. Right? So how do you name that as a substituent?
Amino.
Just simply amino, like you did with alcohol groups that weren't the highest priority. You named them hydroxys. And benzene rings that weren't a priority. You've named it phenyl. You've learned these. It's just another vocabulary word. Right? So here we're just going to name it amino. Right? It's very simple. And where is it?
3.
It's on number 3. And how long is the main chain?
Pentane. Pentanoic acid.
Exactly. So it's a pentane, which we changed the ending to pentanoic acid. Exactly. I don't have to locate that because we know that's going to be number 1, right, by default. So it should have a 3-amino pentanoic acid. Right, so that's how you name these as substituents. Right, one more for you. Highest priority thing you see this time?
The ketone.
The ketone, right. Ketones are higher priority. So the longest chain that includes the carbonyl carbon of the ketone. So it must include this carbon.
It would be pentanone.
Right, so all 5 carbons, 1, 2, 3, 4, 5. And I could count 1, 2, 3, 4, 5 just as well. I don't know which end is number 1 yet. So this is definitely on number what?
3.
3. So it's a, you may have said it and I missed it. It's a pentanone, I agree, but I need to locate it.
So 3-pentanone.
3-pentanone, right. Now there's one more substituent. What is it?
An amino.
An amino, and they got this arrangement correct. You notice the bonds go into the nitrogen, not the hydrogens, unlike our other drawing on the previous slide. So this is an amino on number what?
2.
2, right. So I'm going to start counting from this end, not this end, because I get 3 here either way. Right, so what will be the name?
2-amino, 3-pentanone.
Exactly. Excellent. Right. Anybody have questions on how to do these? The top 2 are when the amine is the highest priority thing, so you have an amine as the parent name. Right? And the bottom 2, the amino group, is just a substituent. So it just gets named as amino. Much like chloro.
I have a question.
Uh-huh.
So it's pentanone because it's a ketone, right?
Correct.
But you don't have to name anything regarding the double bond to the O?
No, that's included in the ketone name.
Okay.
Right? When it's a carbonyl and there's no hydrogen left on it, we name it as a ketone, and that own ending gives that away. Right? We don't name the oxygen in addition to that.
And the CH3 on carbon number 2, you don't have to name that either?
No, because it's carbon number 1. This is not a substituent. This is carbon number 1 of the 1, 2, 3, 4, 5 carbon chain.
Okay.
Much like this one up here, it wasn't a methyl group. It was carbon number 3 of the main chain.
Thank you.
Okay. All right, and then of course we have our benzene special name, right? So you know there's going to be one, right? So when you have a benzene ring with an amino group on it, it gets a special name as well. Much like when we had a benzene ring with an OH on it, we called it a phenol, right? It wasn't a hydroxybenzene, it was called phenol. When we have a benzene ring with an amino group on it, it's called aniline, right? So very simple, aniline. And then you name substituents on that, much like you did with your phenols. So the middle one would be a 2-chloroaniline, because this is by default number 1, where the nitrogen's attached, because that gives it its name. And here we have 2 chlorines attached at numbers 2 and 4, so a dichloroaniline. So very, very simple, very, very similar to the way you did phenols. All right, one more word to your vocabulary list. Okay. So now your least favorite part, and we start talking about isomers. And this one's a little more complicated than the ones you've been doing, because we might have a problem with interrupting our carbon chain because the nitrogen might be in the middle of it. So if you look at this molecule I've drawn, it has 3 carbons, it has 9 hydrogens, right, and 1 nitrogen. And so if you wrote down that formula, C3H9N, and you analyze the number of carbons and the number of hydrogens, then you'll see that it's an odd number. You can't follow the 2n plus 2 rule. And why is that?
Because you have to add a +1 for the nitrogen.
I have to add a +1 for every nitrogen. And since there is a nitrogen, it's 2n plus 2 plus 1. And that comes out to 9 if I have 3 carbons. So that's exactly right. And a simpler way of drawing that is the molecule on the right, which leaves out all the clutter of drawing all those hydrogens, is just a nitrogen with 3 carbons attached, right? We know these are CH3s. You may or may not draw the lone pair. It's okay if you don't, but often you might want to indicate the lone pair for a reason. But that's another way of drawing it. So a much simpler way of drawing it over there. But there are isomers of this. There's no other way I can make it tertiary, because to be tertiary, the nitrogen has to be bonded to 3 different carbons. And since we only have 3 carbons, that's the only way to do it. But what if I said, what are the primary and secondary amine isomers of this molecule? Could you draw it differently? If I said primary, what does that mean?
The nitrogen's only bonded to 1 carbon.
Right, so when you see primary amines, you can treat the nitrogen like you would when you treated putting on OHs, right? It's just going to be an NH2 you attach somewhere. So you would just draw, how many ways can I put 3 carbons together, right? And there's only one way, in a straight line. And where could you put the amino group? Well, there's 2 places. You can put it on the end, or you can put it on the second carbon. And those are the only 2 primary amine isomers of this thing. What if I asked you to make secondary amine isomers? How would you start drawing it? This one's a little different.
You have like 1 2-carbon chain and one carbon chain attached to the nitrogen.
Right, so you've moved on past the question I asked, which is great, but let's try to do things one at a time. You're absolutely right. But I would start drawing a nitrogen and attach 2 carbons to it, right? Not in a row, but 1 on each side of it. And I'd also put a hydrogen on the nitrogen. That's what a secondary amine would be. Then I would ask, where can I put the additional pieces? And by additional pieces, in this case, we just have 1 more carbon. And you can't put it on the nitrogen because we have to keep it at only bonded to 2. And so your only option would be to attach it to one of the other carbons. And since they're symmetrical, that would be the same answer. So those are the answers below. And so here we have our secondary one on the left, where you drew the nitrogen originally with the hydrogen on it, and you put 1 carbon on each side. And then you ask yourself, where could I put the other final carbon? Well, putting it on either one of these carbons would be equivalent, so it's just added to one of them. So this is our secondary amine isomer of this thing. Here are the 2 primary amine isomers. Primaries are much easier and what you're familiar with. How many ways can I put 3 carbons together? Just 1. Put them in a line, right, like this. And then the amino group could be on the end or on the second carbon. Right, so these are all the isomers of this molecule. Right, so when you're doing secondary and tertiaries, you got to first fill out the requirements for being secondary and tertiary. Right, so start with the nitrogens when you're drawing those. Whereas the primaries, you can leave the nitrogens for last because they're just like another group you append to your carbon chain.
And so would these be constitutional isomers?
They would, because the rule for constitutional is something's connected differently, right? So if I were to compare the top one up here with the one below it here, what's connected differently? Or is something connected differently? Yes, so it's a constitutional isomer. More specifically, what's connected differently? Is it the carbons?
The carbons.
The carbons are connected differently, absolutely. Right, so what would this be called more specifically?
Skeletal?
Skeletal isomer, exactly. How about comparing these 2? Right, the 2 on the bottom right. Are they constitutional isomers? Yes, something's connected differently, absolutely. Is it the carbons?
No.
No, the carbons are identically connected, right? 3 in a chain. The nitrogen and the hydrogens are connected differently. So something other than carbon is connected differently. What did we call that more specifically?
Positional?
Positional isomers, exactly. So these terms that you've learned are still useful, right? They're not going away. You're just learning how to apply them under different situations.
But these would not be functional group isomers because they're all amine functional groups, right?
Excellent. That's absolutely right. They're all amines. Some of them are primary, some are secondary, some are tertiary. That's true. But they're all still amines, so they would not be functional group isomers. You're absolutely right. Okay, let's move on to amides. And that's our second molecule for today. It's a little different than the amines. And this is like amines were analogous to alcohols. Amides are going to be analogous to esters. So if you remind me again, what does an ester look like? Right? Or how do we make an ester? What does it look like if you were to draw one?
It's a carbon with like a carbonyl and an ether bond on the same carbon.
Okay, that's a good description. So it's a carbonyl carbon, much like this one here. And on the same carbon is an OR group, right? Of O something else, right? And if it were just an OH, what would you call that?
An alcohol?
No. If it's got a carbonyl carbon, right, like this, carbonyl group, and then an OH on it.
Carboxylic acid.
That was a carboxylic acid, right. So if you look at the top here, this amide, I'm calling it here, is kind of the nitrogen analog of a carboxylic acid. Instead of an OH, it's got an NH2. And why 2 H's? Because nitrogen needs 3 bonds, right? So this primary amide I've written up here. Why primary? Because the nitrogen's bonded to one non-hydrogen thing. So this primary amides are much like carboxylic acids. A secondary amide would have what? This exact structure, who knows what's attached over here, but it would not have 2 H's here, it would have something else on the other side. Right? And that would be analogous to one of your esters. We could also have 2 things attached to this nitrogen, or esters couldn't do that, but amides can. So a tertiary amide would have 2 non-hydrogen things attached here. Right? So they're very analogous to our carboxylic acids and esters. And we named them very simply, much like the way we named amines. So we just dropped the carboxylic acid ending, because this is not an OH, because it's a nitrogen. We just append the ending amide, much like we did amine. Right? So let's do an example here. The simplest one you can have. Right? There's only one carbon. This is clearly the highest priority thing. Remember, amides are right below esters. So this is clearly number 1, by definition, the same way. And instead of saying it's a 1 carbon chain that's an ester, it's a 1 carbon chain that's an amide. So methane becomes methanamide. Right? This one here, the next simplest one, has 2 carbons in the chain. So instead of ethane, it's just ethanamide. Right? So these are fairly simple. The one with the benzene ring in it is very, very simple as well. If this were an OH, it would be benzoic acid, right? We learned that one before. So I'm just changing the OH to an NH2. So instead of benzene, it's benzamide. Right, we dropped the oic acid from benzoic acid and added amide. So very, very simple. Okay, so try drawing this one for me. I want you to draw 3-chloro-benzamide. Well, here's benzamide. The only question is, where's number 3? Now remember, it's a little unique for benzene rings. This is not carbon number 1. It doesn't get a number. It's the carbonyl carbon. This is carbon number 1 of the benzene. So it's kind of unusual when you say 3-chloro. It doesn't go 1, 2, 3. This is 1, 2, 3, because this is 4. Right? So this is number 3. Where do you put the chloro? Or here, either side. Right? All right, so try this one at the bottom. It's fairly simple, straightforward. Find the longest continuous carbon chain that must include and actually start at this carbon.
Would be pentamide.
So let's start with the basic name so we don't lose any syllables here. So it's pentane. We drop the E and add amide.
So pentanamide.
Pentanamide, exactly. We dropped the E and added amide, much like the amines. And there's nothing on the nitrogen, right? There's nothing on this chain. There are no substituents, so it's simply pentanamide. Right? Very, very similar nomenclature to the amines. Right? How about this one? Right? I know the name is there, but try to do it on your own. Find the longest chain. must start here.
Propane, so propane amide.
Right, 1, 2, 3. So propane, and we change the ending to amide. So propane amide. So, and then what's on my propane amide? There's a substituent.
And
A methyl, and its location is in. So I would normally put this in italics, but this figure didn't have it in italics. But in methyl propanamide. Exactly. So it tells me where the methyl group is. If the methyl had been attached over here on number 2, it would have been a 2-methyl propanamide.
question.
Huh?
Do we need to like draw, if we have to write it, do we need to like write it slanted like italics?
No, if you want to write in italics, generally you just underline it. And that would be
Okay.
sufficient to show that, because I can't write in italics either.
Yeah, that would be weird.
So
Okay.
generally we underline it to indicate that it should be in italics. That's a common thing to do. Okay, so this one is a secondary amide. Why am I calling it a secondary amide?
Because the nitrogen is bonded to 2 non-hydrogen atoms.
Right, the nitrogen is bonded to 2 things that are not hydrogen, exactly. Right, and you could also have tertiary ones. Right, this one down below that I have a name for, you try drawing. Right, so I gave you the name this time. You try drawing it. So start at the end. How many carbons in the main chain?
1.
1. And what goes on that carbon? Since it's an amide.
The carbon double bonded to the oxygen.
Right, so you draw your carbonyl. Good. And what else? Since it's
And nitrogen.
and a nitrogen, right? And then what we put on that nitrogen, we'll have to decide in a second. But you would draw your carbonyl, the carbon double bonded to O, and then a single bond from the carbon to a nitrogen. Now we know that nitrogen needs 3 total bonds. So what we'll do next is find out, is there anything on that nitrogen? Yes. So what do you draw on it?
So 2 methyl groups on the nitrogen.
Right, and how many hydrogens would you then have to indicate on the nitrogen?
1.
There would be how many?
None.
None. Right, nitrogen makes 3 bonds. So there would be 1 bond to the carbonyl you drew, and 1 bond to each of the methyls. That leaves no room for hydrogen. So it would just be an N with 3 bonds to it.
Quick question. When does it make 4 again? I'm confused with
It'll
that,
make-
like the quaternary.
It'll make 4 when you have a quaternary ion, right? So we're not going to talk about those too much. I just wanted you to be aware that it can do that. And it would have a positive charge on that nitrogen. You're mostly going to see that with that ammonium ion, not so much in these other molecules. We'll talk about it briefly next time as well, when we introduce proteins. Okay, so that's good. Try the bottom one here. Let's name this. Right, the benzene ring is not part of this main chain at all. So the main chain's over here, where the carbonyl is. So what's the parent name going to be?
SN9.
Right, so ethane. We drop the E and add amide, so ethaneamide. And what's on it?
Methyl, a phenyl.
A phenyl group,
Okay.
yes. And its location?
On 1.
So this is number 1, and this is number 2.
And
It's on
It's
N.
on N, right? It's not on a numbered carbon, it's on a nitrogen. So you put N phenyl, right? Ethaneamide. Right, this is not aniline because this group, this nitrogen, is not the priority anymore, right? It's this whole thing. The amide is the priority, not an amine. Just like you wouldn't call it an alcohol if it's a carboxylic acid. Okay, so here's some links to some things that are really good summaries for priorities and naming. There's many more priority groups that we have not covered, and we won't. That's the end of our list for the basics of organic chemistry. And then if you want a summary of all those pesky benzene names, you know, the ones that I had you learn, here's a good summary of those. I'm not sure if both of these links still work, but they should, one of them at least. And then if you want a bunch of practice problems, here's a link to some practice problems as well, in addition to all the ones I gave you on your practice tests. Okay. And the last thing I want to mention before we end is you should be memorizing your amino acids at this point, right? I mentioned them briefly last time. and I want you to start learning them. And now you see that they are carboxyl groups with amino groups on them. All right, and all these are shown in the form where that amino group has gained an extra proton, which is a proper way to show it. You're never going to find it the other way with this COOH. And we'll talk more about that next time. But I want you to start learning these, and the only thing you need to learn about them, you don't need their pKa's and all those numbers that are under here and sometimes in the figures, but you have to be able to draw them, and you know their names, and they're both abbreviations. The 3-letter, which is rather easy, and the 1-letter, which can be confusing on some of them. Okay, so this is what I want you to learn for your amino acids.